Okay, so when we talk about what it means to be an acid or a base, thus far we've focused on the Bronsted-Lowry theory, and most of the time we're going to do just that. So the theory of what it means to be an acid or base has developed over time. The properties of acids and bases have been known for a long time, but actually, why is something an acid, why is something a base, that definition has changed. Just like our definitions for oxidation and reduction have changed and developed to be more exact over time and more all-encompassing. And so the main definition that you get to focus on is thinking about an acid as a proton donor and a base as a proton acceptor. Okay, and we often even think of a simpler definition, which could be called the Arrhenius theory, about acids dissociating to give H plus and bases dissociating to give OH minus. And then so Bronsted-Lowry is a bit broader than that. But there's actually a third and more all-encompassing theory, which is known as the Lewis theory of acids and bases. And in that theory, acids are electron pair acceptors and bases are electron pair donors. Now, you're probably annoyed when you hear you have to learn yet another theory and another definition that sort of seems flipped from the original definition. But if you think about it, in most other topics in chemistry, we focus on the electrons and how the electrons are being transferred or how they're being shared. That's really how we explain most aspects of chemistry thus far. And so actually, the Lewis theory, in many ways, makes the most sense because it's the most in line with what we've done before. It's also going to allow us to explain the acid-base behavior of some other substances that don't have protons and therefore don't fit into the Bronsted-Lowry theory that we've used up to this point. So a Bronsted-Lowry acid, remember, is a proton donor, and a Bronsted-Lowry base is a proton acceptor. When we look at these reactions, we can see that going from left to right, I see that the NH3 ends up gaining an additional H plus. It gains an additional proton. And therefore, this is acting as a base. And therefore, this is the thing that gave it the proton. And therefore, that is the acid. So I can sort of think about a proton going from here to the nitrogen. Okay. In the reverse reaction, I can think about this H plus going back to the hydroxide. And therefore, this is acting as an acid. And this is acting as the base. And therefore, we've got some conjugate acid-base pairs here and here. So Bronsted-Lowry theory, it's easy. It works for most examples. We could do it one more time. Here's HCl, here's water. As I go to the right side, I now see H3O plus. So the water has gained a proton. In this example, water is acting as a base. HCl is acting as an acid. And on the other side, to return and do the reverse reaction, H3O plus gives away a proton. It's a proton donor, and Cl minus accepts a proton, and therefore it's a base, and therefore we get conjugate acid-base pairs here. So this is the Bronsted-Lowry theory, looking at protons being donated and protons being accepted. Okay? Now, the Lewis theory instead focuses in on electron pairs. So we're going to look at the same reactions, but now we're going to try to focus on what's happening with the electron pairs in these reactions. So Lewis acid, electron deficient species that can accept electron pairs, and it will form a coordinate covalent bond in those cases. And a Lewis base is an electron pair donor. These tend to be electron-rich species, which can donate electron pairs to form coordinate covalent bonds. So Lewis bases have to have at least one lone pair of electrons. And so Lewis bases are really the same thing as nucleophiles. They're actually also really the same thing as ligands. Those definitions sort of overlap each other almost entirely. So when I try to remember the Lewis theory, I first remember that when I hear the word Lewis or the name Lewis, I think of Lewis structures, which makes me think of electron pairs. So it's a helpful way to remember that the Lewis theory is the one that focuses in on what's happening with electron pairs. I then remember or logically think that whatever an acid does with a proton, it's going to do the opposite with an electron pair because protons are positive and electron pairs are negative. So the behavior is probably opposite. That's pretty logical. So a Bronsted-Lowry acid is a proton donor, but a Lewis acid is an electron pair acceptor. So notice that what it did with a proton as a donor is the opposite of what it did with an electron pair. You do have to say pair. You can't say it's an electron donor or an electron acceptor. It's always about pairs. Okay, moving down, if we take a look at these exact same examples, and I try to draw them here with my little marker, I've got my N to H, yada, yada, yada. Here's ammonia. and I'll just look at the forward reaction for the sake of time. I'm going to get there. Okay, so now if we think about what's taking place, instead of thinking about protons leaving the water and going over there, which really we've never done in any other topic in chemistry, we've never focused on just the protons. Let's look instead at the electron pair, something that we would do in organic chemistry, and we'll use curly arrows. So instead of this proton leaving and going to the NH3 to become NH4, I'm going to think about it this way. The NH3 has this lone pair of electrons, which is attracted to this partially positive hydrogen on the water. And so the electron pair from the nitrogen is going to go to that hydrogen, and the electron pair that's holding the hydrogen to the oxygen is going to leave, and it's going to go to this oxygen atom. And so in the end, what we get is the exact same reaction, right? This would form NH4 plus and OH minus. So the same things get formed, but instead of us focusing on what happened with protons, we can now explain it by electron pair behavior. So to me, the NH3 is the one that's donating its electron pair here to this hydrogen. That's what's making a bond with the hydrogen. So this new hydrogen that's attached, that's a coordinate covalent bond. Both electrons came from the nitrogen. And the thing that accepted an electron pair was really the water, because the water took both of these electrons in this covalent bond and ended up accepting them to get the OH minus hydroxide ion. And so notice that this thing before, we called it a Bronsted-Lowry base because it accepted a proton. But now we could call it, it's also a base because of what it does with electron pairs. So it's still a base. Now we just say, okay, it's also a Lewis base. And so one important thing I want to point out is that all these things that we learned as being, bases, like ammonia, it should be in your memory on the list of sort of weak bases that you know. Well, ammonia is still a base under the Lewis theory. The things that were acids and bases before are still acids and bases in this theory. We're just going to define it for a different reason. So this is acting as a Lewis base, whereas water is acting as a Lewis acid. And in the previous page, I said this was a Bronsted-Lowry base and this was a Bronsted-Lowry acid. So those things are the same. And we could do it again with this example, but for the sake of time on the video, I won't. And so the idea is that although we were learning a new theory, all the things that we knew before that were Bronsted-Lowry acids and bases are still going to be acids and bases under the Lewis theory. So why have this new theory? We have this new theory for the exceptions. The things that really, and it's really the exceptions, are Lewis acids. So that's going to be the focus. Things that are Bronsted-Lowry bases are also going to be Lewis bases, and there aren't really exceptions that you're going to need to know. However, there are substances that act acidic yet have no protons, and therefore they cannot act as Bronsted-Lowry acids because you can't donate a proton if you don't have one. So here's sort of the classic example is BF3. There are a few others that you should be aware of also, but BF3 is a Lewis acid, and if we want to know why, we have to look in at the reaction a little bit closer. So if we look at the Lewis structures, we've got NH3 with the lone pair on the nitrogen, and then we've got BF3, which is one of those weird exception Lewis structures where boron just forms these 3 covalent bonds and actually doesn't have an octet. It only has 6 valence electrons now with its 3 bonds to fluorine. Therefore, boron is electron deficient. It can get the octet, but it just doesn't have it in this case. So it sort of needs 2 more electrons to feel entirely stable. And that's why it's such a good Lewis acid. So if these 2 things react and the electron pair gets donated from nitrogen to boron, they'll form a coordinate covalent bond together. And for the sake of it, just know that the Lewis structures stay the same, and now there's a bond between the N and the B. So that doesn't really look like any sort of acid-base reaction that we've seen before. But if we think about it, well, one, it does match our new Lewis theory. So this is an electron pair has been donated, making this a base, and this BF3 has accepted that electron pair, and therefore it's a Lewis acid. But if we think about it in terms of like other properties that we know, how is it an acid-base reaction? Well, the fact is that NH3 is a base, and it's a base because it can donate electron pairs. It's a base because it can accept protons. But if N is now bonded to boron, as it is in this drawing here, now N can't do that anymore. And so if N can't accept any more protons, or if it can't donate any more electron pairs, that is effectively neutralizing NH3. So even though BF3 doesn't look like any of the acids we've learned so far, it neutralizes a weak base. It neutralizes ammonia. And so if you neutralize a base, aren't you an acid? Right? So if you think about it just from the, like sort of the properties, it's a substance that will neutralize a base, so we should think of it as an acid. And now if we try to explain its behavior, well, why is it an acid? We can't explain it based on proton behavior, so we have to look at it, what's happening with electron pairs. And so we'd say boron, or BF3, is an acid because it accepts electron pairs from ammonia, and that's how it neutralizes ammonia. If you want to think from an equilibrium standpoint, if you add BF3, which effectively bonds to NH3 and removes it from the system, well, as a result of removing NH3 from the system, this equilibrium will shift to the left. And by shifting to the left, you're going to make more water, but you're going to make the OH minus amount go down as it shifts to the left. So if OH minus concentration decreases, that will also at the same time bring back up H plus concentration, and pH will drop. So, again, pointing out, by adding BF3 to the solution of ammonia, you eventually will make the pH drop. And if the pH drops, that's exactly what we would expect from an acid. So again, even though it doesn't look like a traditional acid that we've talked about so far, it does have the properties of an acid. It neutralizes a base, and it lowers pH. Okay, a couple other examples to go over quickly. So BF3 is sort of the classic one to recognize as a Lewis acid. AlCl3 is similar. You can also draw AlCl3 with a Lewis structure. Even though you might think it's ionic, AlCl3 has a lot of covalent character to it. So you can draw Al with 3 bonds each to a chlorine. So both of these are electron deficient as they don't have an octet. Some other common examples to be aware of are transition metals. If you think back to transition metals forming complex ions with ligands, it's essentially Lewis acid-base chemistry. These things are very highly positive, they are electron deficient, and therefore they accept electron pairs from ligands, which then form coordinate covalent bonds. So the ligands are the Lewis bases. And so I'll show you an example down below, but transition metal ions actually can lower the pH of solutions, and they do act effectively as somewhat acidic species. These are some other very much less common examples. So I'm not really going to focus on them, but simply to put them out here, these were like some of the electrophiles that we learned in organic chemistry, or that we will learn in organic chemistry, depending on when you're watching this video. And therefore, being electrophiles mean that they'll accept electron pairs, and so they are acting indeed as Lewis acids. So another example, just to show you, here's water reacting with BF3. If they bond together, that leads to water being, this part of the molecule being more prone to giving away a proton. And so eventually this can lead to a pH drop by adding BF3 simply to water. So a solution of BF3 would lead to an increase in the amount of H plus in the solution. Same thing goes here. If you put copper ions in solution, they will bind to a bunch of water ligands and form this complex ion, which we know is why copper 2 is blue when copper is bonded to all these water molecules. Well, being bonded to the copper makes it more likely, to a small extent, for some of those waters to get rid of protons to the solution. So just to focus in on one water molecule as a ligand here, when water is a ligand and this bond is between the copper and the oxygen, it actually makes oxygen have 3 covalent bonds, which is not really what oxygen tends to do. It tends to just have 2, since it has 6 valence electrons of its own. So when water is bound to copper in this way, it makes it somewhat likely for this bond between oxygen and hydrogen to break, and for the electron pair to stay with the oxygen, and for this H to leave as a proton. And so by having these water ligands, you do end up, to a slight extent, remember this is at equilibrium, so this is a small extent these products are formed. But because you are making more H plus, in both of these examples, whether it's BF3 or these copper ions, they lead to pH dropping in the solution, and therefore they do have properties of acids. I'm going to skip over this organic example for now, but this is the nucleophilic substitution reaction that we looked at before. Maybe I won't skip it. If you've got this nucleophile and we focused on its lone pair of electrons, it goes after this carbon, which is electron deficient because of the polar bond between C and Cl, where the electrons are being pulled towards the more electronegative chlorine. As a result, the bond between carbon and chlorine splits, the electrons go with the chlorine, and we formed this ethanol, this alcohol, as a result. So we talked about this as a nucleophilic substitution reaction, but if you think about OH minus as a base, and effectively that base gets neutralized, and so even though we wouldn't think of chloroethane as being an acid, we could also look at it from an acid-base perspective and refer to chloroethane as acting as a Lewis acid because it's accepting an electron pair from the hydroxide, effectively neutralizing the hydroxide when it forms this alcohol. So some last considerations for the Lewis theory. There aren't that many questions on the Lewis theory. You might be asked in like multiple choice to identify which reactions are only Lewis reactions but not Bronsted-Lowry reactions. And in those cases, you're looking for reactions that do not involve protons. So like this first one, because I see the proton going from the HCl to the NH3, this is a Bronsted-Lowry reaction. It's also a Lewis reaction, but it doesn't only qualify in the Lewis theory. Same thing goes for this one. And let's see, same thing goes for this one. So if you're following the H's around, these three all involve proton transfer, whereas these ones don't really look like our normal conjugate acid-base pair Bronsted-Lowry theory acid-base reactions. They involve two things just sort of joining up together. So in those multiple choice, you're looking for the weird ones. You're looking for the transition metals or the D-block metals, ions. You're looking for the ones where two substances simply form a bond together and there's nothing involving protons being traded around. A final consideration also is amphiprotic versus amphoteric. We mentioned these terms before and that they are not the same. So amphiprotic is a more specific term in the way that Bronsted-Lowry theory is more specific than Lewis theory. And so if you're amphiprotic, that means you're an acid and a base in the Bronsted-Lowry, or you can act as an acid and base in the Bronsted-Lowry theory because you can both donate and accept protons. Amphoteric is a broader term. So there are certain amphoteric substances that don't also fit under the umbrella of amphiprotic because they can act as acids and bases, but not necessarily in the Bronsted-Lowry theory. So the best example of that is aluminum oxide. It's one of the period 3 oxides, and you're supposed to know that it is an amphoteric substance, meaning it can neutralize both acids and bases. But it doesn't have any protons, so we can't call it an acid because of what it does with protons, meaning we can't call it a Bronsted-Lowry acid. We can't say it's amphiprotic because it can't donate protons. We can say it's amphoteric because it will neutralize both acid and base if you add them to it. So those are the final considerations for Lewis theory. Mostly what you have to do is pick out Lewis theories. You have to define Lewis acid and base as electron pair acceptors and donors, and you might have to draw out a Lewis acid-base reaction like this, where you show electron pairs being donated and accepted, and you show coordinate covalent bonds being formed. But other than that, it's a pretty small topic in the acids and bases HL section.